Hello, this is Caleb Unger and Nick Losi doing presentation 6 on simulation and finance. The first section basically dives into how Brownian motion works and how we're going to implement it using Monte Carlo. This section of the textbook actually is focusing in on more time series data and how asset or share prices will move across a series of data, and we're using Monte Carlo to best simulate that. So when we're looking at Brownian motion, we notice that it's a stochastic continuous process, and they move according to time or a step called dt, and the Brownian motion is pretty much added to the original state of the value or the asset price that we're looking at. And so when we look at standard Brownian motion, we assume that the first delta time, or dt, is going to be equal to 0, and if we assume that the increments are independent, then we are taking the square root of s and t minus s, or two independent time steps, and we're multiplying those times those weights in order to determine our total Brownian motion. And we simulate through time intervals such that we want n steps across a width of h, which gives us our total t. And basically it sums Brownian motion up as a discrete approximation for a continuous process, as indicated by the equation given with j steps according to the width h that we see there. And you can also include a drift mu or a volatility or scale variance theta to properly express the equation, as you can see at the bottom of this screen. Continuing from Brownian motion, we can dive into asset price movements. We can express these in terms of a growth rate mu, and again a factor of variance or volatility of theta, usually greater than 0, because if theta is equal to 0, then we can express it as the price at a certain time s, which is independent of t, times the exponential raised to the return. The return incorporates that growth rate and is expressed as mu times the second time step minus the first. So then we can express g as a function of x sub t and t. And what this allows us to do is to basically take a partial derivative in respect to our ultimate x, our t, and then our asset price movements. And if we Taylor series expand the function g in terms of all the partial derivatives that we can get, it actually reduces to, again, as you can see, a form of Brownian motion. This time it's just a function of mu, or the growth rate over the variance squared over 2. So when we look further into this, we see that it is Brownian motion, but because it's incorporating these movements and a return, we can call this geometric Brownian motion, otherwise known as asset price movements. The next section delves into what a derivative is and different options that go with derivatives. And it starts out by defining a derivative as a contract that depends in some way on the price of one or more underlying assets. And so we look at a forward contract as one where one party or person promises to pay another specified amount for underlying assets at some specified time. An option is a derivative where the two parties have certain rights, and they're not necessarily required to enforce those rights, though, is the thing. And so when we look at options, we have a European call and put are the most popular, and a European call basically gives the person the right to buy an asset or a share at a certain time and for a certain price, and eventually experience a payoff when it sells at a certain time of either 0 or the original price minus K, which is the specified price, X being the asset price at its expiration date. So then we get into more of the derivative language, looking at the price at the time D of the derivative, which is V, and also the asset with a price of X sub t. And when we look at these, we basically can derive an equation that is in respect to what they call the value of the portfolio. And after taking the partial derivatives and expanding the value of the portfolio, we were able to reduce into the Black-Scholes differential equation. The Black-Scholes differential equation ensures that arbitrage is not possible. And what this means is that there is risk-free profit for those who are entering into this agreement. So after removing the risk-free growth rate, pretty much we are able to come up with this equation, which models the change in the price of the asset at time t for the derivative and the actual price of the underlying asset X to express the overall price of the share movement with respect to an interest rate. So again, the European call allows the user or the holder to basically buy an asset at a specified time or expiration date, which is T, and for a specified price of K. And then we can go ahead and express these relationships. X sub T is the underlying price asset as the equation on the screen, where you can see again the interest rate R, the volatility of theta, and then a random variable Z, and then the final time period minus the current time period you're looking at, and this will give you the underlying asset price. With this, we're able to determine the price at the time t of the derivative that we're actually interested in, which is the equation below. And that again uses the same variables, but is using an expectation according to a normal distribution of X sub t with that same normal variable exponential, but we're subtracting K, or the price we're paying for it, and we're taking the ceiling of that. So with that, we are able to effectively utilize European call to evaluate this scenario of choosing a specific asset at time t for price K. To summarize European put, you're looking at a price of an option in addition to an asset price, and basically you're taking the cost C sub t, or call option, and adding that to a pseudo normal variable, or the price you paid for that option, and that's called put-call parity. You can express it in two ways. Continuous income basically just incorporates an interest rate that is expressed as R sub f, and then you can evaluate the interest earned across the time period as follows on the screen. This changes the boundary conditions and the accompanying equations we just went over to be expressed in a little bit different way, incorporating that interest rate. Lastly, we have delta hedging. This is across currencies, so when you're dealing with different currencies and the risks that are associated with them for the foreign currencies. And as you can see, it's expressed as delta of the prices at time t over the asset price at t, which gives you that equation below.